Okay, last class we talked about circles. Most of that was review in terms of the implicit formula for circle and center and radius. The new part was kind of adding in the parametric equations for a circle. What you will see today is that there are quite a few similarities between circles and ellipses in terms of how we parameterize them and graph them. So an ellipse has a center just like a circle does. The ellipse is centered at the point HK, so that is similar to a circle as well. And in general, the parametric equations for an ellipse are x equals h plus a times the cosine of t, and y equals k plus b times the sine of t. And little stipulation, this is for t values between 0 and 2 pi. And a couple of things here that you should notice. First of all, you'll see that very much like a circle, the center of an ellipse are values that are just basically added on to the parametric equations to basically adjust for moving that center from the origin to another point. You'll also notice these values of A and B, and we'll talk about those in just a minute. And notice that both A and B values are going to be greater than 0. So the first thing that I want you to do on your calculator is I want you to graph these ellipses. This first one, graph it on your calculator, and then we're going to kind of look at what you see. When you graph these parametric equations on your calculator, you should find an ellipse kind of similar to what you have here. A couple of things that we need to now talk through so you can see how the parametric equations turn into some characteristics of our graph. So we already talked about the fact that these values of h, and I graphed this incorrectly. That should be 7, 4 is the center. My bad. I have it at 7, 5, so just move all of this down 1 unit. The center should be 7, 4. Again, those are from our values of h and k. So our center over here is at 7, 4. Now, these values of a and b that are in front of our cosine and our sine, these give you what we call the horizontal and vertical axis. So for that value of 5 that's in front of cosine, what that equates to is what we call the horizontal axis. And actually what that value of, in this case, A gives you is what we call the horizontal radius, because if you look from the center to the edge of the ellipse is a value of 5. Okay, so that's the horizontal radius, is that value of A. And then you would just double that in order to get what we call the horizontal axis, which is just the entire length, which is a length of 10. Very similarly, that value of B, which in this case is 2, that gives you the vertical radius. So you can see from the center we went up and down 2 units. And then the vertical axis then is just double that, which would be the entire thing, that length of 4. Okay, so let's look at how this ellipse compares to the next one we have. So let's take a second to look at the parametric equations. Notice some similarities, notice some differences. So one similarity that we should be seeing is that the center is the exact same, and I'll get it right this time. The center is 7, 4. And then the other thing that we should be seeing is that from the first example here, those values have switched. So think about how that might affect the graph. So if horizontally from the center it's only 4 units across, and vertically now from the center it's 10 units, we can see that our ellipse is now going to be stretched longer vertically. So let's graph this out. Again, our center is at 7, 4. There's our center. And then I'll look at that value of A this time, which is 2. So that gives me how far horizontally I will go. And then I look at the value of B, which in this case is 5. So vertically, 1, 2, 3, 4, 5, I'll plot 1 point, and then go in the other direction. And then that gives me a nice kind of outline to draw in the ellipse. So here, our horizontal axis is the 4 units across, and the vertical axis is 10. Okay. So some notes, just kind of summarizing up what we just discussed. The center, H and K, these are constants. And then the coefficients in front of sine and cosine give our horizontal and vertical radius. And again, those are the values of A and B. And then to find the horizontal and vertical diameters or axis, we just take 2 times A or 2 times B. And really all that means is, so if your value of A is 5, that's quote unquote the radius, then the diameter would just be double that, is all this is saying, okay? Okay, now looking at parameterizing an ellipse, this is going to again feel very similar to what we did with circles. So if you look at the first one, we definitely want to draw out our picture. We have an ellipse centered at the origin, crosses the x-axis at plus or minus 5. So here's 5 and negative 5. And then it's crossing the x-axis at positive and negative 7. So draw that in. Now what it doesn't tell us that we're going to add in is that we are going to go clockwise starting at 0.50. Okay, we're going to go in a clockwise direction starting at 0.50. So again, this is going to be very, very similar to our thought process on finding the parametric equations for a circle. We have our x equals and our y equals. Now, since the center is at 0, 0, we are not going to have values for h and k. If you really want to put zeros in to kind of keep that straight for yourself, that's fine. So let's look at this point 50 in the direction that we are going. So if we think about the x value here, this is the biggest x value, so it's at the max, and it is going to be decreasing. Well, that follows what cosine does normally, so we're going to use cosine here. And then the only other thing that we have to add in is that horizontal radius as a coefficient, which in this case is 5. For y, our y value is at the midpoint, and we are going down. So because that y value is at the middle point and is decreasing, we know we need to use sine, but sine typically increases there, so we're going to make that negative. So this is going to be plus a negative sine t. So there are the parametric equations. So really the only difference between what we do for circles versus ellipses is that you have to consider those lengths, so those different radius. For a circle, they're always the same, which is what makes it a circle, but for an ellipse, we just add in for x, the horizontal, for y, the vertical. Let's look at another one. All right, so we're centered at the origin again, so we don't need to worry about h and k. It says it crosses the x-axis at 3 and -3, y-axis at positive and -7. So a skinny, tall one. So again, x and y for our equations. Again, since the center is on the origin, these are both 0 and 0. Okay, for this one, it says that we are tracing counterclockwise, starting at -3, 0. So I'm starting here at -3, 0, going counterclockwise. Okay, so let's think through. Our x-coordinate is at the minimum, and it is going greater. So this is basically cosine flip to get to the minimum point, and then we add in that radius. So it's going to be plus a -3 cosine of t for that horizontal radius. For the y value, I am at the middle, so there's sine, but we have to look at where we're going. I'm going to the decreasing from the middle, so that's going to be a negative sine as well, and then just adding in that vertical radius, so -7 sine of t. All right, last little bit here is looking at the implicit formula for an ellipse. The implicit formula for an ellipse centered at HK with a horizontal axis 2A and a vertical axis 2B is given by x minus h squared over a squared plus y minus k squared over b squared equals 1. So again, similarities between circles and ellipses. The only difference between the formula for a circle and ellipse are these values. So if you take those away, you basically have a circle. Adding these in, those the a squared and b squared, that is what kind of stretches it either vertically or horizontally. So then what we are going to do in the last example is we are going to complete the square similar to what we did with a circle to get this written in standard form. What we are going to do is group the x terms, which they pretty much already are, group the y terms, and then I like to move my constant to the other side. So I have 4x squared plus 16x, I'm going to leave some space, plus y squared plus 2y, I'm going to leave some space, equals -13. Now, the other thing that I need to do also, because I have that leading coefficient, I do need to factor that out before we complete the square. We don't need to do that with our y's. All right, now we can complete the square. So half of b squared, adding 4, But again, because you have that leading coefficient, that's not really 4, that's really 16 when we add it to the other side. Completing the square for the y's, half of 2 squared is plus 1, so add that to both sides. Now we can factor. So for the x's, I have that coefficient 4, and then this factors to x plus 2 squared. My y's factor to y plus 1 squared, and then I'm adding over here to get 4. Then the very last thing I need to do, if you notice in the general form, there are no coefficients up here with those square terms. So what we're going to do is divide everything by this coefficient of 4, and that will give us the formula that we're looking for. So this 4 over 4 is now over 1. This y plus 1 squared stays over 4, and then 4 over 4 here is 1. From here, we can get the information that we need in order to sketch. So our center is going to be -2, -1. Plot that. Now we need values of A and B. Again, those are the values that give us how tall and how wide. So if you notice, the A value is squared underneath our x factor. So if we take the square root of this, that gives us an A value of 1. So horizontally, I'm going 1 point in each direction from the center. And then under the y factor is b squared. So if I take the square root of that, gives me the vertical radius that I need, going 2 in each direction. And then we just graph that in. I did a poor job of that. Let's try it again. Graph that in. There we go.